Namaskar and welcome back to Concrete Engineering and Technology, where we are talking of different aspects of this subject which have acquired importance in recent years. We were talking about some mechanisms of deterioration in concrete, and we had identified or decided that our discussion will be confined to reinforcement corrosion in concrete, alkali aggregate reaction, freezing and thawing, treatment of chloride penetration in concrete, and carbonation. Within the subject of reinforcement corrosion in concrete, chloride penetration plays a very important part, and let us review what we did in the last lecture. We said that we will look at reinforced concrete as steel bars embedded in concrete, and concrete itself would be basically considered a conglomerate of coarse aggregate embedded in mortar, and the cement paste would be the integral part of the mortar as shown here, and would comprise of solid CSH and pore spaces. So, as far as chlorides are concerned, they will be sitting either in the pore spaces or in the cement or in the chemical compounds of the solid hydration products. These are the things that we will talk about today, but this is a recap of what we did last time. We had also discussed why iron in normal conditions embedded in concrete does not corrode, and that is because there is a dense film of gamma iron oxide which is formed on account of the high pH in the concrete or the environment immediately surrounding the reinforcing bars, and this high pH is the result of the formation of large amounts of calcium hydroxide in the hydration of the constituents of cement, that is C2S, C3S, C3A and so on. We had also talked about the fact that basically reinforcement corrosion in concrete is either chloride induced or carbonation induced, and in the case of chloride induced reinforcement corrosion, the passivating film is damaged even though electrochemically the environment itself does not change, that is the passivating film can theoretically thermodynamically still remain stable. Whereas, in the case of carbonation induced reinforcement corrosion, penetration of carbon dioxide leads to the consumption of calcium hydroxide, which lowers the pH of the pore solution, and therefore, the passivating film around the reinforcing bars, which is stable at high pH, becomes unstable, and therefore, we have a destabilized passivating film, and with the passivating film gone, the surface of the iron is open to attack from oxygen and water, which is present in the concrete. Now, in the class today, we will confine our discussion to different aspects of chloride penetration in concrete, how the chlorides move into concrete, and how are those processes modeled, what are the parameters involved, and so on. So, getting started with our discussion, let us recall that chloride induced reinforcement corrosion can occur in any structure if the construction material such as sand, water or admixture contain chlorides, and that is why our codes and standards lay down specific limits on what is the maximum permissible chloride content as far as sand is concerned or water is concerned, admixture is concerned, and so on. Marine structures such as offshore structures, ports and harbors, structures near the coastline, they are all susceptible to chloride induced reinforcement corrosion because of the presence of sea or salt in the sea water. Similarly, structures with de-icing salt applications in cold areas are susceptible to reinforcement corrosion because there the chloride ions come in the form of de-icing salts, and the structures in that category would be highways and bridges in cold areas, parking garages, which are themselves covered, but cars coming from highways and bridges with the de-icing salt in their tires and the underbelly, that is deposited on the slabs of the parking garages, and those the reinforcement there is rendered susceptible to corrosion. Now, let us take a look at the concrete in chloride rich environment a little more closely. We have a cover concrete and we have chloride rich environment outside. There has to be an equilibrium, a physical equilibrium between the chloride content in the atmosphere and the chloride content in a thin layer of cover concrete just outside here, which is near the surface. The chloride in the environment has to be in equilibrium with the chlorides present in the pore solution in a very small thin layer which is close to the surface. So, we are further dividing the cover concrete into a thin layer of cover concrete which is in contact with the atmosphere, and the normal cover concrete which is somewhere here, and of course, there is different from the main body concrete shown beyond the reinforcing bars, and the passivating film of course is as shown. It should be remembered that this thin layer and whatever chlorides it contains serves as the source of chlorides for ingress inside. So, what really happens, or at least the way the models are constructed are, so what really happens, or the way the models are constructed, they assume that the chloride rich environment is in equilibrium with the surface layer of concrete, and that surface layer of concrete serves as the source of chlorides for the penetration of chlorides further into the cover concrete. So, once that distinction is clearly understood, we can proceed further and understand this as a diffusion process. What we are looking at is something like this, that there is a thin layer of cover concrete, then as time goes on, more and more chlorides penetrate from this surface layer inside the concrete, and what we have is a cover concrete contaminated with chloride ions. The concentration of these chloride ions could be different at different points in the cover concrete, and it stands to reason to believe that as we go deeper into the concrete, the extent of penetration of chloride ions will be lesser, that is, the concentration will be lower. The concentration of chloride ions in concrete is generally expressed as a percentage by mass, that is kilograms of chlorides to a kilogram of concrete powder, or sometimes expressed as kilograms of chlorides per cubic meter of concrete. Different units are used depending on what is our convenience. So, we can convert one from the other because we know the density of concrete and all these other constants. So, we can proceed with that. Having said all this, we must also remember, where does the chloride ions establish themselves? Where do they physically occur? If we look at this picture, which shows the pore spaces and the solid hydration products, and this picture which shows coarse aggregate or fine aggregate, depending on whether you are looking at mortar or concrete, whether it is this thin layer or it is the cover concrete at large or it is the main body concrete, all these concretes have essentially this structure, and therefore, the chlorides from the atmosphere, that is this environment here, they have to move into concrete through these pore spaces, and some of these pores need not be connected, and therefore, they will not contribute to the ingress of chloride ions into the concrete, but basically the chloride ions move through these pore spaces and move inside, and this thin layer has a similar structure The chloride concentration in the thin layer should be in equilibrium with the chloride concentration in the chloride rich environment. We must also remember that this whole process of chlorides moving into concrete occurs when the concrete is wet. Most of this diffusion process, most of this ionic movement, in fact all of this ionic movement to some extent takes place only through aqueous medium. There is no movement of ions if the concrete was perfectly dry, and the same argument holds if the environment had perfectly dry sodium chloride or any other chloride, it will not be able to move into the concrete. As far as engineering is concerned, in all cases, whether it is marine structures or it is de-icing salts or it is a swimming pool where chloride or it is a swimming pool where chlorine has been used for keeping the water clean. In all cases, there is water involved, and therefore, what we are really asserting is that the water in the environment, which is chloride rich, and the pore solution, they have to be in equilibrium as far as chloride concentrations are concerned. That does not mean that the chloride concentration in the concrete will be the same as the chloride concentration outside. Please remember that chloride concentration outside, that is in the chloride rich environment that we are talking about, is in terms of percentage of chloride ions in water, whereas the chloride ion concentration in concrete is not given in terms of chloride concentration in the pore solution, because it is virtually impossible to extract pore solution and then try to measure the chloride concentration there. We will come to that discussion a little later, but it must be clearly understood that chloride concentration in concrete is expressed generally as a percentage or in terms of kgs of chloride per cubic meter of concrete, as we talked before. And therefore, to equate and therefore, to establish an equilibrium between the chloride concentration in the chloride rich environment and the chloride concentration in concrete is only a conceptual construct and not necessarily a very simple numerical issue. Now, let us look at chloride ion ingress into concrete. What we are seeing is that this is the surface layer or the thin surface layer that we are talking about. In that thin surface layer, we are assuming that the chloride concentration remains the same, is virtually constant, and the reinforcing bars are placed at a certain distance away from the surface, and that is called the cover. And what this figure is showing is the progressive ingress of chloride ions into concrete with time. That is, to begin with, maybe there was no chlorides inside, and we could almost draw a straight line like this, that there is no chlorides inside, except that the thin surface layer has a certain amount of chloride. With passage of time, more and more chlorides move into the concrete, with the surface layer acting as the reservoir. With the passage of time, what we find is that at a given location from the surface, the chloride concentration keeps increasing. And now, as far as our previous model in terms of corrosion initiation is concerned, we should understand that chloride concentration in the neighborhood of the bars should not be allowed to exceed the critical level within the service life of the structure. So, if we have a certain critical chloride concentration level, that is that concentration level at which the passivating film is damaged, then what we need to ensure is that at the location of the bar, that is at the cover depth, the chloride concentration should not be allowed to exceed this critical level in the service life of the structure. Sooner or later it will be exceeded, that is no doubt true, but it should not be allowed to happen within the service life of the structure, and that is the principle of performance based durability design, where we say that yes, we understand that this structure is susceptible to corrosion, it is susceptible to chloride penetration, chloride diffusion. We have designed it such that the chloride concentration at the location of the reinforcing bar at the end of the service life will still be lower than the critical chloride concentration. Now, this process of chloride ingress into concrete is often modeled as a concentration gradient driven diffusion process, and that in mathematical terms is given by a differential equation which is given here. We are not going into the mathematics of deriving this equation, and the solution of this equation is a form which is given here. So, the equation 2 is a solution of equation 1, and this is the so called well known Fick's law. What it says is that the chloride concentration at a given location is related to the depth, time, the surface concentration and the diffusion coefficient. And this build up from here, that is with the increasing time, more and more chlorides get into the concrete. This phenomenon, if it is represented as a concentration gradient driven diffusion process, these curves can be represented through this kind of an equation. It stands to an argument, we can discuss it, whether or not chloride penetration in concrete is indeed a diffusion process, or it is a concentration gradient diffusion process alone. For example, in concrete, it is not only the chlorides which are moving, in certain cases water also moves in and out of concrete. Consider the case of parking garages or de-icing salt applications, where the concrete surface is not really exposed to the same amount of chloride concentration all the time. It is not even exposed to water all the time. Only when it snows or when the snow melts or it rains, the surface becomes wet. In other cases or at other times, it remains dry. The same thing is true in marine structures, where part of the structure which is submerged is always wet, it is always under the action of, it is always wet and submerged in the sea. There is a tidal zone, there is a splash zone, and there is a zone in the concrete structure which remains clearly above the sea, and the kind of chloride environment there is quite different. So, it stands to reason to say that all the chloride penetration does not occur through a concentration gradient diffusion alone. Experts and researchers in the area understand this, and therefore, the only model that is most easily available and can be applied is the diffusion model, and that is why it is common to use it. One is free to use another system, another framework which replicates the natural situations better. Looking at this equation a little more closely, Cxt is the concentration of chloride ions at a depth of x from the surface after time t of exposure. C0 and T are the surface chloride ion concentration and the coefficient of diffusion of concrete, coefficient of diffusion of chlorides in concrete. Now, we must remember that the basis of the formulation of this equation is the fact that the concentration gradient diffusion process governs, and that C0 and D are constants over time 1 and at different locations of the concrete structure for another. These assumptions are very fundamental in nature and have implications which an engineer must understand. So, for the time being we will leave it be at that. We will proceed to take a closer look at the coefficient of diffusion T and the surface chloride concentration C0 in this equation. Now, as far as the coefficient of diffusion is concerned, this factor is essentially the ease with which the chloride ions can move through the concrete. That is, if this pore structure here was very dense, very tortuous, very fine, then the ease of movement of the chloride ions will be low. It will be difficult for chloride ions to move in a structure which is very fine, very long winded, tortuous and so on, compared to a structure which is open, large and so on. And this ease or this pore structure is related to the kind of factors given here, the water cement ratio, the cement type, the cement content and so on. It is also the level of saturation that could be critical. As I have said before, there is no ionic diffusion expected in dry concrete. So, depending on the water cement ratio, the cement content and the cement type, we will have different pore structures which will be formed as represented here. And if the pore structures are different, the ease with which the chlorides can move into concrete will be different. And that is why our codes and specifications try to put down numbers on what is the maximum permissible water cement ratio or the minimum amount of cement content and so on, when we try to ensure durability of concrete. Indirectly, what we are saying is that we are trying to control the diffusion coefficient of the concrete. In practice, the chloride diffusivity can be estimated using diffusion cell type tests. It can be done through a rapid chloride permeability test, it could be done through a ponding test, or it could be estimated from the chloride concentration profiles of different concretes. We will take a look at them one by one. Let us take at the diffusion cell setup. This is a classical diffusion cell, where we have a concrete block. One side is NaCl, the other side is pure water. It could be calcium hydroxide containing no chlorides to begin with, and over a passage of time what we expect is chloride ions to move through the concrete and start appearing here. And if we are able to sample the water here over a period of time, what we will find is that the chloride ion concentration will rise. And as far as mass balance is concerned, yes, if this chloride concentration rises, the kind of chloride concentration here will fall, except that in most cases the concentration here is so high that the decrease here is rather small. Also, we must understand that when the chlorides move through the concrete, some of the chlorides are also in transit and they are occurring within the concrete, and they have to be accounted for if you really want to do the mass balance. This is the flux, that is the amount of chlorides or the chloride ions that are moving in a certain time. So, there is an area which is involved, there is a diffusion coefficient involved, there is a concentration gradient in terms of delta C by delta L, where delta L is this length here and delta C is the difference in concentration of chloride ions at the two ends. T is the time between observation, and flux is obtained from the change in the concentration in pure water chamber over the time t. So, once we understand all these numbers, then we know the flux as to how much chloride has moved in, we know the area of the concrete specimens that we have, we know delta C, we know delta L, we know T, and we can actually estimate T. So, this is one method of estimating the diffusion coefficient directly. It is a very tedious process, it could take several months depending on what is the size of the specimen that we take, what is the nature of the concrete that we take, and so on and so forth. Coming to the next test, which is the rapid chloride permeability test, the RCPT. The details of this test are available in the ASTM C1202 and ASTO T277. I am leaving out the exact test methods given in these two documents, and what we can look at. We can look at this test as an accelerated version of the diffusion cell setup. The RCPT test looks something like this, where we have an NaCl solution and an NaOH solution on two sides of a concrete disc, and on both sides of the concrete disc we have these conducting plates, and we apply 60 volts of DC across these two conducting plates. So, it is basically the diffusion cell setup with the addition of the conducting plates and the application of 60 volts of DC for a period of 6 hours. And what we do, as I said, the details are available in the ASTM C1202. The disc that we use of concrete in this case is known to be 100 mm diameter and has a thickness of about 50 mm. The discs need to be vacuum dried and then kept immersed in distilled water. This ensures that all pore water present within the concrete is removed and is replaced by pure water. The discs are set up with NaCl and NaOH on either side as shown, and 60 volt are applied across the two faces of the discs, and the current flowing between the faces is recorded, and the total charge, that is I and T, that flows over a 6-hour period is taken to be representative of the chloride permeability of the concrete. Instantaneous values of current need to be recorded frequently, and what we get at the end is something like this, that we have with us a certain amount of charge that has passed for a particular disc. A disc of 100 mm diameter, 50 mm thickness, across which 60 volt was applied for a period of 6 hours, and the current that is going through is recorded frequently, and it is integrated over time to give the charge passed, that is in coulombs, and what we have is a certain number of coulombs, and the interpretation is to be made in terms of how much of coulombs do we get, and ASTM 1202 suggests that the chloride diffusivity may be taken as high, moderate, low, very low or negligible, depending on what the coulomb values are. So, basically what the test has done is that the chloride diffusivity or the chloride permeability has been taken as related to the passage of current through the concrete. Of course, as far as interpretation of these results is concerned, depending upon the age and composition of the mix, it may become difficult to impress 60 volts of electricity as required in ASTM 1202, and there are papers in literature where tests have been carried out at other voltages and the results need to be referred to. Effort has also been made in literature to correlate the coulombs with other properties of concrete, such as porosity or oxygen diffusivity, strength and so on, because at the end of it what we are trying to measure is related to the porosity. It is not porosity itself. Porosity itself is measured in terms of volume of pores in a given volume of concrete or in a given mass of concrete, but the diffusivity is also related to the porosity. So, we are making an indirect assessment of porosity through this process, and we are trying to determine that using the passage of current. and those coulombs will have some kind of an indirect relationship with the other parameters such as strength, oxygen diffusivity, porosity and so on, and efforts have been made in literature to relate these parameters also. Coming to the third method that may be used to estimate the chloride permeability, we have ponding of concrete. In this case, a concrete specimen is prepared and a chloride solution is just allowed to stand on the concrete surface. And after a passage of time, the chloride concentration at a fixed depth from the surface is taken as a measure of the diffusivity. So, we take a slice as shown here at a certain depth from the concrete surface. We need to take a core first, take a slice at a certain depth and find out the chloride concentration in that concrete. When we compare the chloride concentration at the same location for a concrete A with that in a concrete B, if the chloride concentration in concrete B is higher, then it stands to reason that that concrete B has a higher chloride diffusivity. What this method does is not give you a quantitative number in terms of the diffusion coefficient, but helps us rank different concretes in the order of chloride diffusivity. This method can also be used to study the effectiveness of a coating. If there is a system or some method by which we want to coat the concrete here and say this coating is such that it will prevent the ingress of chlorides into concrete. So, this kind of a method will become very handy in determining how effective is the coating which has been applied at the surface. Coming to another method where diffusivity can be estimated, that is using the chloride profiles, that is distributions. We need to obtain the concentration at different depths and find the C0 and D, so as to obtain the best fit for a given time of exposure through an iterative process. What this method really says is that we know, or we somehow are able to obtain the different chloride concentrations at different depths from a concrete structure or a concrete specimen, whatever we are dealing with. If we have a concrete specimen like this, which has been exposed to chloride environment for a certain amount of time and so on, and after that we take a sample out of this, make a core, make slices and determine the chloride concentration at different depths. So, as we come deeper into the concrete, the concentration will go down, and once we have those numbers and we plot chloride concentration versus depth, and we assume that the concentration profile should follow this equation, that is C of x t should be C0 times 1 minus error function x upon 4 root of 4 dt, then for the different x's we know different c's, and that is what is indicated here. At x1 it is C1, at x2 it is C2 and so on. And since we have several of these points, through an iterative process, a numerical process, we can try to estimate the values of C0 and D. So, we can get the theoretical value of the surface chloride ion concentration and also the diffusion coefficient for this concrete based on the values that we had. Efforts have been made in literature to relate water cement ratio, which is known to be the most important parameter as far as porosity is concerned, or for that matter the cement type, and we will find that if we collate the information about the diffusion coefficient from different sources, we will get a scatter which is of the nature shown here. It is not a very promising sight. It does not augur very well to a student who sees that there is virtually no relationship between the water cement ratio and the diffusion coefficient. But then this is only to a start. What we must understand is that this data has been taken from diverse sources, experiments carried out under diverse conditions and so on. And we need to work a lot more and get better information about diffusion coefficient and its relationship with parameters such as the water cement ratio or the cement type and so on. Now, let us come to the surface chloride concentration and try to understand that part a little bit better. So far as concentration gradient diffusion is concerned, only the chlorides in the pore solution need be considered, because it is only the chlorides which are present in the pore solution that move because of concentration gradients. Engineering judgment shows that the total amount of chlorides in the cement paste or in a concrete is much different, is higher than that is physically possible if we consider the condition that the pore space and the pore solution has to be in equilibrium with the chloride solution outside. The amount of chlorides that we have in concrete is much higher, and therefore, we are forced to assume that a lot of chlorides are actually sitting trapped partially or fully in the hydration products, that is in the CSH gel. And now, once we understand or assume that the chlorides can be present in different forms, fine, we will say that the total chlorides is what we are trying to work with, and what should be the number that we need use in the formulation of our problem. The Japan Society of Civil Engineers has suggested the following values in terms of kgs per cubic meter that may be used till such time as a better approximation becomes available. In tidal and splash zones, number may be taken as 13, in coastlines it can be taken as 9, and depending on what is the distance from the sea, the number can be taken to be different. As far as vertical, as far as the height of the structure is concerned, it also suggests that a meter of vertical distance may be taken to be equivalent of 25 meters of horizontal distance. These numbers are engineering approximations based on observations and are now being worked out for greater accuracy, and the people across the world are trying to understand chloride concentrations and chloride penetration in concrete better and apply it for engineering decisions. As far as the concrete, now let us try to look at the different states in which the chlorides can exist within the concrete. One is fixed within the hydration products of the cement. This is very likely to happen in cases when chlorides are present as part of the constituent materials. At that time, the hydration products are only being formed, and if there are chlorides, those hydration products will be formed along with the chlorides. In other words, the chlorides will become a part of the hydration products. Then, of course, there are chlorides in the pore solutions, and they are basically free chlorides. And finally, there are loosely bound chlorides on the walls of the pores, and this is what is diagrammatically represented here, where we have a pore, and this is a large pore which is partially saturated with water. So, we can say that this much is water and this is, let us say, air, and within the pore solution we have these chloride ions which are in solution, and therefore, they are highly mobile, These are the chloride ions which are trapped chemically in the hydration products, and these blue ones are chloride ions which are loosely bound, or they are adhering to, or they are adsorbed on the surface of the pore walls, and they can be called into solution, or they can move into solution and go back to their adsorbed state depending on whatever is going on inside the pore structure. As now the question is, which of these chloride ions are really harmful from the point of view of reinforcement corrosion? As far as deleterious ions are concerned, it is argued that the chlorides fixed in the hydration products are not likely to cause any harmful effect as far as corrosion is concerned. The argument is as follows, that if we have a surface like this and a reinforcing bar here, chlorides which are fixed in a location something here like here, which is not very close to the reinforcing bar. These chlorides, so long as they are fixed in the hydration products, have no bearing on whether the bar will corrode or not. Therefore, a differentiation is sometimes made in terms of total chlorides and soluble chlorides. Total chlorides in concrete are determined by extracting the chlorides with something like nitric acid. We take a powder of concrete, boil it with nitric acid, and all the chlorides which are there come out as ions, whether they are in hydration products, whether in pore solution or adhering to the surface or whatever. In the case of soluble chlorides, we do not want the chlorides which are bound in hydration products to appear or come into solution, and therefore, the extraction is with water. There are methods to do it. They are standardized in terms of for how long should the water be allowed to agitate, as to how long the process should be allowed to go on, whether there should be stirring, boiling and so on. But the moral of the story is that at the end of it, it is difficult, but the bottom line still remains that the total chlorides are the most important chlorides, and as far as engineering judgment is concerned, they are the only parameter that can be used in terms of comparing with the critical chloride concentration. Now, coming to another parameter, which is the critical chloride concentration that causes the onset of reinforcement corrosion. Based on tests including fresh concrete, accelerated tests and so on, values in the range of total chloride content of 0.3 to 0.6 kgs per cubic meter have been reported. Investigations based on more realistic environment have suggested values in the neighborhood of 1.2 to 1, have suggested values between 1.2 and 2.4 kgs per cubic meter, and the JSCE has endorsed a value of 1.2 kgs per cubic meter in the hope that the number will be revised as more information becomes available. Now, how do we determine this value? We determine this value by tests such as immersing a steel bar in a saturated calcium hydroxide solution, which is a popular medium to represent pore solution, and have a varying amount of chlorides in that saturated solution, and test the bar at the end of the test using electrochemical methods, visual inspection or loss in weight and so on. We must also try to look at the effect of flexural cracks. When we have a concrete beam, we also have sometimes some flexural cracks in the beam, and these flexural cracks promote faster chloride penetration into concrete, and whether or how this flexural cracks affect the chloride penetration is something which an engineer should be aware of, and this is what we are looking at. We have a certain width of flexural cracks, we have a certain spacing of flexural cracks this causes local damage around the reinforcing bar, and it is likely to damage the passivating film again in the neighborhood of the cracks. So, the keywords in this kind of a study would be surface width, that is the width of the cracks at the surface, the spacing of the cracks, subsidiary ingress. Subsidiary ingress means this is what is primary ingress, because that is what is being controlled by the water cement ratio and the strength of concrete, the porosity of concrete here. But as far as penetration of chlorides in these parts is concerned, is not occurring through the main body concrete. It is first going through the crack, and then from here onwards a certain amount of penetration is taking place, except that this crack spacing in most cases is quite small. Most of our codes do not allow cracks higher than say 0.2 mm or 0.3 mm, and that too if there are aggregates within the crack does not look all that open as is shown here, and therefore, this penetration from the cracks is indeed what can be called subsidiary ingress. The amount of corrosion that takes place on account of all this is also related to the extent of tension in the bars, that is what is the tensile stress in the bars. So, one of the methods of controlling the crack width and therefore, subsidiary ingress and therefore, chloride levels at the reinforcement location and therefore, finally, the reinforcement corrosion is to control the allowable amount of tensile stress in the reinforcement, and of course, the cover thickness besides concrete properties, that is water cement ratio, strength and so on and so forth. Now, if you look at chloride ions diffusion in cracked concrete, this is what really is happening. So, parts of this diffusion process here is through the main concrete, part of this diffusion here is not main diffusion through the main concrete, but is coming through the cracks, and what we have is hardly a one dimensional diffusion. Normally, we assume chloride penetration in concrete to be a one dimensional diffusion process, and that is why if you recall, we saw the equation which looked like del 2 C by del x square is equal to d times del C by del t. So, this del 2 C by del x square basically assumes a one dimensional diffusion process, which is hardly the case if we look at a system like this, where the diffusion is definitely not a one dimensional process. But then again it is a model. So long as the cracks are fine, they are very small in width, an equivalent diffusion coefficient can be calculated by multiplying the diffusion coefficient d by some method, maybe 1.5 or 1.3 and so on. And finally, we want to find out the time to corrosion, which can be the time to corrosion, which will be determined by a graph like this, which says that well, at the end of service life t, the chloride concentration at the location of reinforcing bars, that is at a depth L from the surface, for a given concrete which has a diffusion coefficient d, will reach either the critical chloride concentration itself or just a fraction below that. And as far as design is concerned, what we need to ensure is that the chloride concentration at L at the end of the service life t should be less than the ClCr, that is the critical chloride concentration. And this can be done by having a combination of the cover L and the diffusion coefficient d. Either we can increase the cover or we can reduce the diffusion coefficient, or a combination of these two methods. So long as we do that, we will be able to have a durable structure. So, this is what the basic principle was, that there is an initiation time and there is a propagation time, and if we do not want to bother about the propagation time, because of engineering considerations, and we want to confine ourselves to the initiation time, then we need to follow. Then we need to have the strategy which we just discovered, or we need to follow the strategy that we just formulated, that is, at the end of service life, the chloride concentration at the location of the reinforcing bar should be lower than the critical chloride concentration. Now, before we close the discussion today, I would like to leave some questions. What is Friedel salt? We talked in terms of chlorides being fixed in hydration products, and that should give you a hint as to what is Friedel salt. The second question which I would like to leave for you is how can the values of the surface chloride concentration and the coefficient of diffusion be determined from the chloride concentration profiles. In the discussion today, we just said that given a concentration profile with a certain number of points, we can do it in an iterative manner. Please try to see how actually that iteration process will work. Can the values of the surface chloride concentration and the coefficient of diffusion be taken as constant? They are taken as constant, yes. They may be taken as constant, that is also another yes. But what are the implications of doing so? Is it realistic? Is it not realistic? And so on. From available literature, try to study the difference in the chloride concentration profiles for different environmental conditions, different cement types and different water cement ratios, and you will get the kind of results that I showed you in one of the pictures. They will give you information about chloride concentration profiles from different kinds of environments. If we take a structure or a sample from a highway which has been exposed to 10 cycles of de-icing salt every year, and the sample has been drawn after 10 years, the chloride concentration profile there would be quite different from a marine structure where the sample or the core has been taken from the submerged part of the structure, or the tidal zone, or the splash zone, or a structure which is away from the coastline. The distance to the coastline may be 500 meters, maybe 100 meters, and there if we try to take the concentration gradient or the concentration variation of chlorides within concrete, these are the kind of things that we need to study and assimilate, bring them together on a common platform, and then try to figure out what really is happening as far as chloride penetration in concrete is concerned. With that, let us close the discussion. Thank you.